I'm guessing that this is another set of test points for some test fixture so that they can enable the row drivers without actually having everything assembled. Or it could just be access points for a bed of nails type tester that would go through this and make sure all the LEDs were there and they were put in the right way around. Sort of a big fancy multi-headed multimeter. So anyways, after that 120 ohm resistor, let me just gently bend these back into place now that I'm done. One thing to watch out on 220 package parts is this thermal slug here is connected to the collector, in this case, of the transistor. So if you bend these just right and this touches that, you'll short two rows together, which would be bad. This top corner LED input comes down to a row of test points and then comes over to pin 3 pins in on that chip. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pin 10. Now, 7406s, if I look at my cheat sheet here, that's a hex open collector buffer. And the interesting thing about it is it's a high voltage open collector buffer. So this particular part, even though he's running on 5 volts and his inputs are 5 volts, you can have a pull up from this part to plus 30 volts and it won't damage this part. It'll be able to drive that 30 volts to ground long as you don't exceed the input current or the output current ratings of the part. So this leads more Creed to the fact that they were running the LEDs at a higher voltage than they're running the rest of the cards so they could get more brightness out of them. Now, they could either be running it at higher than 5 volts because that's what you need to get maximum brightness, or they're running it at 5 volts or less so that you could dim the display down by lowering the voltage to just the LEDs. So that was 7406. Let's grab the pin out for that guy real quick. 7406. And the also interesting thing is it's not an LS part. This is the plain Jane 7406. Okay, pin 10. Pin 10's an output, which we expected, and pin 11 is its input. Now this is an inverting buffer, I do believe. So where's the little truth table? Yep, there's the truth table. So Y equals not A. So the output is inverted from the input, which is also indicated by the little circle on the output. So there's the output inverting. I also put a little OC, which stands for open collector. So if I go back later and look at this, I know exactly what I'm dealing with where. And that comes in pin 11. So this is basically just a bus voltage isolator. It allows a 5 volt TTL signal on this side drive a questionable voltage on this side, either higher, lower, or the same, to turn this high side PNP transistor on to drive the whole row of parts. Okay, so now we need to trace pin 11, which is not on this side of the card. Right there it is. So pin 11 goes over to this chip, one over from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. Pin 9. Well, that's a 273 again. How do I want to draw this? Starting to get a little crowded up in that corner. I have to name buses through. So it's a 273. I already looked at the data sheet for this guy once, but let's pull it up again and grab the where pin 9 goes. So pin 9 is an output, so that matches up with what I expected. Comes out pin 8, or comes in pin 8 and goes out pin 9, if you're looking at the flow of data. So at this point, this is the core of the LED circuit that's repeated multi-billion times on this card. Speaking of which, I know it's 8 rows because that's easy enough to count. 1, 2, 3, 4, 5, 6, 7, 8. But how many LEDs long? Now, I could just count them all, but quite frankly, I'd probably lose count before I was done. So instead, I'm hoping it's some standard, spacing. Okay, unfortunately, it's not, 100,000s or something like that. 329. I wonder if that's 3/8. Okay, I got 3. Nope, that's not close enough. Unfortunately, I might just have to count them all. And I'm really not looking forward to that. Oh, there's the little marks. I might have counted all these already before once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 groups of 8. 6, 36, 96. Yeah. So I have a 96 by 8 matrix. Now, if we assume that this is all used as frame buffer, how many full screen messages could we fit in there? So 1024 times 2, and if we assume that they used the full width of this bus, 8 bits, to drive one row, divided by 96 columns of LEDs, you could have 21 full screen messages sitting in the buffer. So you'd have, if this was one screen, you could have 21 of them stacked edgewise, and you could then address through memory to scroll the message on by shifting the address space this way. Scrolling up and down would be more difficult because you'd have to pick the 21 bits in there and then shift data up and down. It wouldn't just be a direct copy from memory anymore. That right there, the shifting up and down, might be a key indicator that the micro is always in the way in the middle. It wasn't just the micro wrote the image to the memory and then the micro had a little ISR routine or something that just popped a window between memory and the latches to say, okay, display this bank of memory on the display. Now, it could do both, but I'm guessing if they went through the work to process image data as it was coming in, that they just did that for everything. So, but 21 screens of data, that's quite a bit. I think that would be sufficient for all my needs, other than the fact I'm chaining 2 of these together, but I get another 2K of memory off the second sign, so maybe I can tie those 2 together and make one big sign that just scrolls out of memory. I need to sit down and think of what exactly I want in my feature set. Definitely want to be able to display a fixed image, scroll an image this way, but I don't know how much if I want to scroll down or scroll up, because that will add significant complexity to the code. So what's next? Looking on the back of this guy, we have this little mess of wires here, which is this ground which seems to only serve the LEDs. It hits all the transistor drivers here, loops around this edge here, and the only other place it's used is by these 3 transistors down here, which looks surprisingly familiar to those. My guess is this little group of LEDs here is an identical set from a driver point of view as this group up here. It's just they physically moved the LEDs down into this corner, and so there's 3 rows of 8 made out of this little cluster. Makes sense. You know, why come up with something unique for these LEDs when you already have a programming interface for all the rest? There's also a 373 or a 273, sorry, right there. So that's probably the latch. That's the driver, and then the row and columns, you know, just come off this end and wrap around here. I don't plan on ever reusing these LEDs because they're sort of out in matrix, and I don't know what you do with them across the room. So this will all go away, is my plan. There's also this white wire in this bundle, which goes over to this corner and into that chip. Nope, sorry, that's a bunch of resistors. So it goes into right there, which is the first device, which is a diode. On the other side of that diode, it's a couple parts and that guy, which is a cap. Okay, so they made a little filtered power supply there. Hits a bunch of resistors, and then goes into this guy, which is an LM10. LM10, I don't have it on my cheat sheet because I forgot to get it the first time. LM10 is basically a pair of op amps in a little can package. Now, the package style, you don't see canned ICs like this too much anymore. I mean, you don't even see canned transistors too much anymore. It was a semi-expensive packaging style, very robust, very good heat dissipation characteristics, but expensive to make. So basically, all this guy is you know, an op amp like this in a little metal can with legs going down in the card. Why they chose to use a part in a can versus a regular plastic part, I don't know. Maybe at the time when they built this, it was only available in a can. So you have a op amp, input-output, and you also have a second op amp with a fixed voltage source on the one side of it. Now, what that is useful for is you can power this chip off of a rail, and then also detect when that same rail goes below a certain set point. So if I look in the data on this guy, somewhere in here it should state what that voltage offset is. And I do not see it at this time. Reference, right here it is, 200 millivolts. So what you can do is take your power supply rails, divide it down so that at 200, so when your rails are good, they're above 200 millivolts, and then when it droops down to the point where you need to stop something from happening, maybe reading, writing memory, or refreshing the display, that voltage will drop below 200 millivolts before bad things happen in the logic in your card, which will cause this output to flip. So my guess is this is a voltage supervisor that watches the power coming in through the main connections, and then as it starts to droop, it shuts down the micro, so it stops reading and writing this SRAM, which takes a lot of current. When you read or write a SRAM or any logic gate, that's when you take the most current. It's when you're switching states. So if you quiesce the bus and stop all access to those devices, they will use quite a bit less current, and therefore cause, this one I already took the batteries off of, cause your leaky batteries that were over here to last longer. So my guess is this input was one of the voltages needed to make this op amp operate. And it might have been minus. Let's see if we can figure that out. So this little tab here is pin 1, and it's 1, 2, 3 around the edge. So there's pin 1, 1, 2, 3. That's actually the positive input to the op amp, unless I miscounted. There's the tab, which is pin 8, so 1, 2, 3, 4. 4 is V minus. So, does this have a square pad? No, it doesn't. So, 1, 1, 2, it's definitely pin 3, and then pin 4 goes to that resistor, which goes all over the place. Yeah. So that's the positive input. So, I'm not fully sure what this white wire is for yet. It's an input to an op amp. It's fed through a bunch of stuff. And it comes into here, it gets fed through this bunch of diodes and resistors, and then into an op amp. It's some sort of it's got to be some sort of analog input. Maybe it controlled the dimming. I just don't know at this point, and it'd be hard to trace out. Anywho, back to where I was at. These two here is the main power supply for the LED matrix. So if I go and stuff 5 volts at a lot of current through them, I should be able to get some LEDs to light up. This grouping here looks to be the logical voltage for the sign. Now there's 2 separate sets of power coming in here. The 2 black wires just go to this big honking ground trace that feeds all the logic. So more than likely we can follow this thing all the way through. Now there's a positive lead going into this little circuit right here, which is called S+. Now, not exactly sure. Okay, it looks like S+ feeds the logic gates for sure. S-. And then this other wire comes in, it's just labeled as +5. Now, comes in here, goes through what looks to be 2 diodes, and that's definitely a diode. And this one, oh, you can just barely make out the shadow of the band on this end, so that's just a bigger, higher current diode there. Now, why do they have so many separate domains on this? I don't know. I can guess. It might be that they wanted the ability to power up certain parts or keep certain parts alive when power failed. This path here definitely is a higher current path because much bigger diode, and all the writing has gone off of, which sort of tells me that it gets hot, or used to get hot quite a bit. Little diode here, it hits a few spots. There's a filter cap and a bleed resistor, and that feeds over to a little selector right here. You can either pick +5 or SB. I'm guessing SB stands for standby maybe, and that +5 pad goes back to this diode. So this is like +5 rail here. Here's standby. It might be standby. And that feeds over to... Boy, it just sort of runs the gamut across the card. Right here. Okay, that seems to feed the SRAMs. So this looks to be SRAM voltage right here. Now we have this battery backed up circuit